Once we understand stoichiometry, the concept of calculating how much each reactant can make can be used to compare different reactants to see which one makes more or less of the product, to give us a true value of how much we can make when we have a mixture of two or more things. So we're going to use the term limiting reactants to just try and figure out which one makes less. And these next two pictures are going to show the example of this balanced equation with nitrogen and hydrogen in a 3-to-1 ratio. How much ammonia can we make? And then before the reactants over here, you can see that I have a perfect 3-to-1 ratio. Everything is evenly arranged, so all of these are going to react to make products. So when we look at this reaction, we get the same picture, but we have our 3-to-1 ratios here of the nitrogen and hydrogen, but I have some leftover nitrogen. So the total amount that I can make is not just dependent on one reactant, but both. Which one is going to run out first? Not necessarily which one you have less of, because the hydrogen here, I have more of it, but it's running out faster because it's 3-to-1 ratio, and that's going to determine how much product I can make. And you can see that these two nitrogens that are left over are still there at the end, left unreacted. So we're going to calculate those things mathematically when we have mixtures of more than one reactant. Here's a multiple choice question with some of the choices somehow missing. Which of these is going to give me the greatest amount of product? So to do that, we kind of have to look at these, and we'll call this B and C. It's a multiple choice. We need to compare how much can the hydrogen make and how much can the oxygen make in each scenario to see which one will run out first. And we're just comparing them to the product. I'll put that arrow back down here. And realizing that there's 2 hydrogens make every 2 H2Os, so it's a 1-to-1 ratio for the product, but every 1 oxygen is going to make 2 H2Os. All right, so let's take this one at a time. Choice A, 2 moles of hydrogen. We look at that separately. That has the ability to make 2 moles of water. Okay, then we look at the oxygen. I have 2 moles of oxygen. Well, that has the ability, it's a 1-to-2 ratio, that has the ability to make 4 moles of water. So if the hydrogen can make 2 and the oxygen can make 4, I cannot really make 4 because I won't have enough hydrogen. Hydrogen's going to run out after I make 2. So the answer to A, how much can that mixture make, is I can only make 2 moles of water. Okay, because we're trying to make water here. B, 2 moles of hydrogen. Again, that's going to give me 2 moles of product. Oh, let's change the color there. 2 moles of product. Now I have 3 moles of oxygen. Well, that's going to give me 6 moles of water. And I don't want water, or we don't want, I can't make more than 2 because of the hydrogen. So again, the oxygen is going to be my excess. The hydrogen is going to run out, and the hydrogen determines how much I can make. Again, we have 2 moles of hydrogen. That's going to make 2 moles of water. And now I have 1 mole of oxygen. Well, that's still a 1-to-2 ratio, so that 1 oxygen is going to give me 2 moles of water. Well, those are equal. They're both going to run out at the exact same time, so I can make 2. No, one isn't limiting or excess. And we say, okay, from the hydrogen here, now I have 3 moles of hydrogen. Well, that's going to allow me to make 3 moles of product. But I only have 1 mole of oxygen, so it's a 1-to-2 ratio. That oxygen is only going to let me make 2 moles of product. So in this case, my hydrogen is excess, and in all of these scenarios, these are both equal here, I am only able to make 2 moles of water. They all produce the same exact amount. Now I wrote hydrogen and oxygen here, but this is really, we're making water from those 2 ingredients. So the question is still how much water can I make? That's what we were talking about here. But this just keeps track of which ingredient has the potential to make each amount of water. But those were in moles, and this example is in grams. So this is going to get a lot more challenging when we get questions like this, because we have to do a lot of stoichiometry. sodium hydroxide reacts with phosphoric acid to give sodium phosphate and water. If I have this many grams of sodium hydroxide and 15.4 of phosphoric acid, how many grams can be formed of the sodium phosphate, and how many grams of the excess remain unreacted? And then we have a yield question at the end. Okay, so here we go. This is going to be challenging here. I'm going to show you two ways to solve this. The first one is definitely more preferred because it's going to answer all of these at the same exact time, and it's going to give us a tool that we're going to use later in the year. So let's first get our balanced equation. 3 sodium hydroxides plus H3PO4 is going to make sodium phosphate and a 3PO4 and 3 H2Os. All right. What we need to do here, we kind of take a little inventory. We have 17.8 grams, 80 grams with sig figs, and then 15.40 grams of sodium or phosphoric acid. And we need to know how many grams of sodium phosphate can we make. What we're going to do is we're going to keep track of all of this in a chart. Since we know that 3 to 1 to 1 to 3 ratio there in the balanced equation, those are mole ratios. So if we just keep track of everything in moles, how many moles of everything do we have? We can kind of do some bookkeeping and see what these ratios are going to be, how much of each one is going to go away. So convert these to moles, and I'm going to put a B here for before the reaction. How is it going to change, and then what is happening after the reaction? And these are all going to be in moles. So if I convert 17.8 grams of sodium hydroxide to moles, 0.445 moles. 15.4 of the phosphoric acid is going to give me 0.157 moles. You look at those and you say, okay, 0.157 is smaller, but it exists in a 3 to 1 ratio. So we can't just compare these and say, hey, which one do I have less of? You definitely can't compare the grams. We need to compare the moles, and we need to standardize them or reduce them so that they have the same coefficient. So there's two ways we can do this. I'm only going to show you the easier one. Since this is going to react in a 3 to 1 ratio, it's going to disappear 3 times faster. Let's just kind of pretend that these numbers, let's reduce them down to a coefficient of 1. We can do that by dividing them by 3 to get a value here. We know that this one is going to change by 3x. It's going to disappear 3 times faster than this one here. And my product is going to up here by positive x. So we think about this algebraically. We're not going to really do the algebra here because it's going to be, we'll know what x is here in a moment. But this is how we want to think about the coefficients. The sodium hydroxide is changing 3 times faster than the phosphoric acid. They're both going down. And the sodium phosphate is going up by a 1 to 1 ratio. So we always treat the coefficient of 1 as x. So let's find x. We do that by reducing our original mole amounts by their coefficients until they're coefficients of 1. So our coefficient of the phosphoric acid, this is my hypothetical x, is 0.157 because it already has a coefficient of 1. My x value for the sodium hydroxide would be the 0.445 divided by 3 because it's going to go away 3 times faster. So if we want to compare it, let's divide it by 3. And that's going to give me 0.148. Okay, so we compare these. Only one of them is the real answer. It just gives me a way to compare them. Which one do I have less of? Which one is going to disappear first? And when we see the 0.148, this is a smaller amount than this, so that is going to be my real x value. This is going to be my limiting reactant. I'm going to have some of this excess since I have more of it. So we need to use that number. The x is 0.148. Okay, and that's going to help us solve the rest of our problem. That's going to see what goes away. If you get the x values wrong, when you do this, you'll have okay. If you do this wrong, once you actually go through the math, you'll have a negative answer, which is not possible. So if you do that wrong, just know that you got your x value wrong. Maybe you missed a coefficient or something. Since we know that the sodium hydroxides are a limiting reactant, 3x, that's kind of how we got that number anyway. We know this one's going to go to 0. There will be no sodium hydroxide left. But now I can subtract here and say how much phosphoric acid do we have left? Well, if we subtract x, 0.00867. Okay, and my x value here, my sodium phosphate, is going to be 0.148. That is my x value. Now those are both in moles, but it answers two questions at once. It says, what's my limiting reactant? A couple questions actually. How much of my excess is left over? And how much product can I make? All that's left is going to be convert these to moles. So how much excess do we have left? 0.00867. I think that's the second question, but let's just go ahead with that one. This is moles of H3PO4. We just need to convert that to grams. That has a molar mass of 98, so 1 mole, 98 grams. And that's going to give us 0.850 grams left over. Okay, it's going to make me downsize everything. If we do our second one, how much product can we make? Well, now that one is 0.148 grams of Na3PO4. Sorry, that is moles, not grams, because that is our mole chart. And we look at that molar mass. 1 mole is going to be 163.94 grams. And that's going to tell us that we can make 24.26 grams of Na3PO4. And then our last question is, if the actual yield was 15 grams, what's the percent yield? So there are goofy calculations for this that you'll never have to do. If you just remember a percentage here, if the actual yield is 15, what is the percent yield? Well, percents are just parts of the total. So my actual here is 15 grams. I'm supposed to make 24. We just calculated that. I should be able to make 24, but I only made 15. What is my percentage of that? Well, 15 over 24.26 times 100 is going to give us a 61.83% yield. Okay, don't make percents more complicated than they have to be. But that answers, if you can figure out how to do this mole chart when you're given more than one ingredient, you don't necessarily have to do stoichiometry. We're going to use these charts later in the year a lot, but you can just kind of keep track of the changes a little bit algebraically with the moles and the coefficients. That's going to be very, very useful. Another way to solve that problem, if you're more comfortable with the stoichiometry, is to just do a couple stoichiometry problems. So you can answer them with 3 stoichiometry problems, but you need to know how to read them. Okay, so the very first problem is going to be, let's convert our sodium hydroxide. We've got 2 ingredients. Two ingredients, the sodium hydroxide and the phosphoric acid. Let's rewrite our balanced equation here. 3 sodium hydroxides H3PO4 makes Na3PO4 and 3 H2Os. Okay, because we're going to need that. So the way to do this is to take both ingredients, convert my sodium hydroxide to phosphoric acid, convert my sodium hydroxide to sodium phosphate, and my phosphoric acid to sodium phosphate. If I do these two separate problems, then I'll have an answer. How much can I make? Whichever one makes less, that's how much I can make. But I do have to go through two full stoichiometry problems. So this is going to be 40 grams per mole of NaOH. This is going to be a 3-to-1 ratio, 3 moles of NaOH to 1 mole of sodium phosphate. And then every 1 mole of sodium phosphate is 163.94 grams. Okay. And then secondly, so that's going to give me, let's just get that answer, 24.32 grams of sodium phosphate. Second thing we need is the phosphoric acid. We've got 15.4 grams of the phosphoric acid. Phosphoric acid, H3PO4. Every 98 grams per mole, every 1 mole of H3PO4, this is a 1-to-1 ratio now, is going to give me 1 mole of sodium phosphate. And the sodium phosphate still has the same molar mass as before. Don't recalculate it twice. 163.94 grams. Okay, that's going to give me 25.76 grams of sodium phosphate. Okay, so we look at these and we say, okay, how much sodium phosphate can I make? Well, my sodium hydroxide has enough to make 24 grams. My phosphoric acid has enough to make 25. Once I make 24, we will run out of sodium hydroxide. We can only make 24 grams, 24.3 grams, which is within sig figs about the same answer as we got on the last slide. That makes the sodium hydroxide limiting. There will be none left, and it makes the phosphoric acid excess. So the question now is how much phosphoric acid will be left? Most people with this method are tempted to just subtract these two answers, but these units are not in phosphoric acid. This is sodium phosphate. This is an excess amount of sodium phosphate that doesn't even exist, so you really don't want to deal with this number. That's not how you read these stoichiometry problems. What you need to do is ask another question. The last question is going to be, since sodium hydroxide is limiting, how much phosphoric acid will it use? So that's going to be our last conversion. Sodium hydroxide, take our limiting reactant and convert it to the excess reactant. Okay, so here's our third problem. We take our limiting reactant, the 17.8 grams sodium hydroxide, 40 grams per mole. And then we need to convert that. For every 3 moles of sodium hydroxide is going to give me 1 mole of phosphoric acid. We're converting it to the excess because I want to know how much of that I'm going to use. Now we already have the molar mass of the excess reactant. Don't recalculate it, 98 grams per mole. And that's going to give me a value of 14.54 grams. And this is where you have to read what these numbers are. You can't just blindly calculate them. Okay, so what does that number mean? Well, let's go back to our problem and see what we have here. We have available in the problem 15.4 grams of the phosphoric acid. That's my excess reactant. We just calculated that we only need to use 14.54 grams. That's what this number means. Once my limiting reactant runs out, how much of the excess reactant is going to go with it? Let's make that H3PO4 so we remember what that number means. We're going to use 14.54. So how much is left over? Well, when we subtract those, we get our leftover amount, 0.863 grams of the H3PO4 left over. Now the sig figs are a little bit different. You get a slightly different answer this way versus the other way, but it's not really within the magnitude of error. So it's totally fine depending on which way you use and how you round it along the way. But you need to know how to use one of these methods. The first one we're going to use more commonly at the end of the year, so keeping track of everything all at once is really useful to see how things react and disappear. But if not, then you need to do separate stoichiometry problems and learn how to read what will, if I do this conversion over here, what will that tell me? What do those numbers mean? Because you can't just calculate the numbers, you need to understand what they mean so you can answer the questions.